Today, I like to discuss a very important instrument which is called the refrigerator, and it is the now household kitchen appliance. Its market name is fridge. So this actually any substance, whenever it is tried to cool, that process is known as refrigeration, and the instrument or the machine or the contrivance by which this cooling process occurs, it is called a refrigerator. And the working substance used in this refrigerator is called refrigerant. And the functions of this refrigerator, I like to state here the Carnot refrigerator, which works in this same fashion as this Carnot engine works, but in a reverse way. Let us see the picture. Here it is LTR, lower temperature reservoir, and it is the high temperature reservoir, and it is the refrigerator. So it is the three parts, HTR, LTR and the refrigerator. And this in this case, the heat is withdrawn from this LTR. LTR here is the refrigerator inside of this refrigerator, and HTR is the environment in which this refrigerator have been kept, which is at a high temperature. And heat is extracted, suppose say Q dash, heat is extracted from this LTR at this lower temperature to this higher temperature. Naturally, this process is not spontaneous. Reverse process is spontaneous. Heat will flow automatically from this high temperature to lower temperature, but according to the Clausius bar, or in our direct experience, heat will never pass by itself from this lower temperature to this high temperature. So this is why we have installed one machine which is the refrigerator, and work has been put in this refrigerator from this electrical source. From this electrical source, this work is done on this refrigerator, and a refrigerator, in that case, this non-spontaneous process becomes spontaneous. It is just like, you can say, the heat water, like water pump. Water pump, in case of water pump, this water lift the water from this lower level to this higher level, and this water pump is run by the external energy. Sometimes it is electrical energy, or by sometimes the combustion of this diesel. So this is also, refrigerator is also some sort of, like water pump, it is a heat pump. It takes up heat from this lower temperature and rejects this heat, or thrown this heat to this high temperature reservoir by the applications of this external work on this refrigerator. The mechanism or the working formula for this refrigerator is same as the Carnot cycle, but in reverse fashion. Suppose this is the Carnot cycle. Here I have already drawn. In case of Carnot cycle, it will start from A, B, C, D and A. But in case of refrigerator, it starts from D. it starts from D, D to C, C to B, and B to A. And then from A to D, it comes to its initial stage. And here this Q dash amount of heat is taken by this refrigerator from this lower temperature reservoir T dash, and it rejects the heat at a high temperature, rejects this Q amount of heat at this high temperature T. And the formula or the steps will be similar to Carnot engine. Here D to C, you see this here D to C, it is isothermal, reversible, expansion. Expansion volume is increasing from V4 to V3. So it is the first step D to C, it is reversible isothermal expansion from volume V4 to V3 and at a temperature T dash. T dash is the temperature inside this refrigerator or this LTR. So the first law, whenever we like to apply the first law here, Q equal to W dash, here Q dash plus W1 equal to delta U. But delta U equal to NCV dt equal to 0, as this gas is ideal gas. This relation is valid for the ideal gas only, and temperature is constant, so dt equal to 0, so du equal to 0. So this Q dash equal to minus W1, this is the work done in the first step for this expansion, and it is N or T dash ln V3 final volume by initial volume, this equation number 1. Then it is the second step, C to B. C to B is again this adiabatic compression, volume is decreased. So no heat is supplied to this process, to this second step, and the reversible adiabatic compression from V3 to V2. Temperature, whenever this adiabatic compression occurs, the temperature will rise from T dash to T. And naturally the first law of thermodynamics, this heat given 0 or heat exchange is 0 plus W2. W2 is the amount of work done in the second step and equal to delta U, or W2 equal to delta U NCV T minus T dash, the final temperature minus initial temperature, and CV is the molar heat capacity. And here the working material have been taken as N moles of this ideal gas. So it is NCV T minus T dash, equation number 2. Then third step B to A. It is again isothermal, reversible compression. Reversible isothermal compression from V2 to V1 at this temperature T. So in this case, the equation, first law equation, Q plus W3 equal to 0, delta U equal to 0 for the ideal gas at constant temperature. So Q equal to minus W3 equal to N or T, here temperature T at which this process occurring, and ln V1 by V2. V1 is the final volume, V2 is the initial volume, so equation number 3. Now last, we are coming to the last step, A to D. A to D, reversible adiabatic expansion from V1 to V4, and the temperature, whenever the adiabatic expansion occurs, temperature falls from T to T dash. And so this first law, again Q equal to 0 plus the W4, amount of work done in the fourth step, equal to delta U. or W4 equal to ANCV T dash minus T. T dash is the final temperature, T is the initial temperature. So W4 equal to minus NCV, and T is taken first, T minus T dash, the equation 4. So these are the 4 steps, and 4 amount of work is done in 4 steps, and the total network, total work, network done, W equal to W1 plus W2 plus W3 plus W4. But you can see this W2 and W4, these are equal in magnitude but opposite in sign. So these two are cancelled. So this W equal to this W1 plus W3, and putting these relations here, this W1 equal to minus ANR T dash ln V3 by V4, and this W3 equal to minus ANR T ln V1 by V2, or W equal to minus ANR T dash ln V3 by V4, and if we take it a plus, then ANR T ln V2 by V1. But already in my last class I have shown that V3 by V4 equal to V2 by V1. These 4 volumes are connected, and this is the relation. So instead of V2 by V1, I can write here V3 by V4. So taking this common, A and R will get common, ln V3 by V4 will get common, and T minus T dash. And Q dash, which is the heat taken by this refrigerator from this LPR, it is equal to ANR T dash ln V3 by V4. So ANR T dash ln V3 by V4. So the performance of this refrigerator, performance means this energy output, energy here it is energy input. W is the energy input given to this refrigerator, and Q dash is the energy output of this from by this refrigerator. So the energy output divided by energy input, this is called performance of this refrigerator. It means that how much this refrigerator can extract from this LTR by applying the 1 unit amount of work. And this one here, W is taken as positive. W is positive, as this is greater than this one. V3 is greater than V4, and N is positive, R positive. So this W is totally positive. It is a general rule. If the cycle works in clockwise, then W will be equal to negative. But here refrigerator run in anti-clockwise. Whenever it is the anti-clockwise, say anti-clockwise, then W becomes a positive. This is a general rule, and also this has been proved here. Refrigerator, amount of work required, amount of work given to this refrigerator, and it is positive. And also the cycle runs anti-clockwise, so it is positive. So this is all about this refrigerator. So cancelling Q dash it is, and W this one, and this one, and whenever this ratio have been taken, it is T dash by T minus T dash. So this efficiency, or I can say here the performance of this refrigerator depends on the temperature of this source and sink. Performance of the refrigerator it is given the symbol E. This psi equal to T dash divided by T minus T dash. So it is similar to this heat pump, but slightly differs from this heat pump. In case of heat pump, suppose this is the room where in a cold region, sometimes it is required to warm this room by the use of this heat from this outside source. And so here suppose heat pump and this Q here this surrounding, here it is the interior of this room, room, and in this interior Q amount of heat is again thrown to this interior from this surrounding, and Q and this W amount of what is given to this heat pump. It is usually done in whenever you like to warm a room, and so the if performance of this heat pump equal to naturally how much heat is thrown to this interior by this amount of work applied. So this is the input, this is output. So here Q divided by W. So it is Q divided by Q minus Q dash. So in terms of temperature, it is T, and here T minus T dash. If you can see, then performance of this heat pump is a little bit greater than this performance of this refrigerator. Say psi performance of this HP equal to Q by Q minus Q dash, and it is here. So this one equal to Q dash plus W divided by Q minus Q dash, and this is equal to this Q dash. Here you can write this W, Q minus Q dash equal to W, work input to this refrigerator or this heat pump. So Q plus W and divided by W equal to Q dash minus W plus 1, and this one is the efficiency. This one is the efficiency of this or performance of this refrigerator. So the performance of this HP equal to 1 plus performance of this refrigerator. This is not only the working formula for this refrigerator, but it is equally applicable to this AC, air conditioner, in cold storage, and everywhere when this substance has to be cooled. I am giving here a sketch of this refrigerator. Here I am giving a sketch of this refrigerator. Here, a simple sketch or the line sketch of this refrigerator. And this is the wall of this refrigerator. Everyone, I think, know or have seen this refrigerator in the kitchen. This is refrigerator. And the refrigerator has four components, four parts. One is the compressor, one is the evaporator coil, and here is the condenser coil, and here the expansion device. That means 1, 2, 3, 4. These are the rack in which the substances are kept, or foods are kept, which have to be cooled. And outside of this wall, these walls are insulated so that heat cannot be exchanged from this within this refrigerator and the surrounding. And the first step I can call here, suppose D. Here the working substance have been taken as a trade name R410A, which is difluoromethane and pentafluoroether mixture. This is the working substance they used in the refrigerator. And this working substance have been taken here at this D at a very cold temperature. This is in the form of liquid at very low T and low pressure, low temperature, low pressure. This substance have been taken in the form of liquid, and this liquid is passed through this evaporator coil, and evaporator coil is kept within this refrigerator, inside of this refrigerator. So actually, this whenever the supercooled, the liquid is passing through this coil inside this refrigerator, it is getting evaporated. It is getting evaporated at a constant temperature. Whenever this liquid is evaporated, it draws this latent heat from Q dash. It has been taken, or this Q dash amount of heat is taken by this coil in order to vaporize, and this substance which have been kept inside this refrigerator have been cooled. So here this liquid now becomes this vapor, and vapor coming directly to this compression. This is adiabatic compressions of this vapor of this working substance. By the compression, adiabatic compression, pressure is also increased, temperature is also increased. Temperature suppose increase about 90 degrees centigrade. Pressure suppose pressure is equal to the 8 atmosphere, suppose, and temperature is suppose 90 degree centigrade. For the sake of simplicity or to explain, these data are given here. So the compressor will do the compression, and pressure is high, temperature is also high. It is passing through this coil. This is condenser coil. This has been kept outside of this refrigerator, by the side of this refrigerator, under this atmosphere. And so when this vapor, high temperature, high pressure vapor passes through this coil, here the temperature, suppose room temperature is 40 degrees centigrade, and here the temperature is 90 degrees centigrade. naturally this vapor will be cooled down. Vapor now becomes condensed into liquid. Vapor now condensed into liquid at this temperature 40 degrees centigrade. Pressure remains the same. Now this cooled liquid is passing through this expansion device, and here this lower pressure there occurs a pressure difference. Here the pressure is 8 atmosphere, and here this pressure is suppose 6 atmosphere. So there is a pressure. So this liquid rapidly under adiabatic conditions, this liquid rapidly cools down, and even a small amount of liquid is vaporized under this adiabatic expansion, and this liquid, whenever vaporized, it again takes the heat from this liquid, as it is the adiabatic system, adiabatic expansion. So liquid becomes more and more cooled, and whenever this liquid is passed through here, and it is about suppose say minus 20 degrees centigrade. So this very low temperature, this liquid is again passing through this evaporator coils, and the process is getting repeated to cool down the substances which are taken, which have been kept inside this freeze. So this is the D. This is D, starting from here D. By this evaporator, it comes to this position C, and C2B, it is the compressor, adiabatic, reversible, not reversible fully, adiabatic compression done by the compressor, and this compressor machine is connected by this electrical arrangement, electrical plug. And this compressor takes this electricity from this electrical plug and performs this work. And so from B again it is coming to A, isothermal and isothermal compression, isothermal expansion. B2A, this one is isothermal expansion. B2A, isothermal expansion, where this liquid, where this vapor becomes into this liquid at its room temperature, say 40 degrees centigrade. And A2D, again it is adiabatic expansion. By this adiabatic expansion, this liquid becomes more cooled, and this liquid is passed through again this evaporator. This is all about the rough sketch and rough explanation how the refrigerator works, how this refrigerator cools down the substance which are of the substances which are kept inside this refrigerator. So actually this working formula is also equally used in case of the air conditioner. And whenever you try to buy one air conditioner, you have been asked by this seller how much ton of AC you like to purchase. So the AC or the any refrigerator heat pump is expressed in terms of this ton capacity, and 1 ton means 1 ton AC. 1 ton AC means, suppose this is a room. This is room, and here some container. Here some container, and if you keep 1 ton ice at 0 degree centigrade, then at this room temperature the ice starts melting, and the amount of heat taken, latent heat taken for the melting of 1 ton ice at 0 degree centigrade and 1 atmospheric pressure to liquid water at 0 degree centigrade and 1 atmospheric pressure, the amount of heat extracted in a day, amount of heat extracted, it is equivalent to 1 ton AC. So this process is 1 ton ice at 0 degree centigrade and 1 atmospheric pressure, and here the 1 ton water. 1 ton water at the same 0 degree centigrade and 1 atmospheric pressure. The amount of heat required, for this conversion in a day is called the 1 ton capacity. So 1 ton actually numerical value 1 ton. Here it is one short ton is used. Short ton. 1 short ton is equal to 2000 pound. 1 short ton is equal to 2000 pound, and the latent heat required actually 144 British thermal unit per pound. For 1 pound of ice will be converted into 1 pound of ton at this 0 degree centigrade and 1 atmospheric pressure. 144 British thermal unit is taken from this source, from this environment, and so this will be equal to 144 British thermal unit in a day. In a day means 24 into 60 minutes. So this will be equal to round about 200 British thermal unit per minute. But one British thermal unit equal to 1 British thermal unit equal to 252 calories. So this one equal to actually 50.4 kilocalorie per mole per minute. So this device, 1 ton AC means it will extract this heat 50.4 kilocalorie from this room in which this AC is installed per minute of a time. So this is the all about the working formula of this refrigerator, and you can put a simple equation, simple problem. One problem you can do here. Suppose this refrigerator is working. Refrigerator is working between minus 10 degrees centigrade and 30 degree centigrade. What is the performance of the refrigerator? refrigerator. If 1000 calorie of heat is to be extracted, how much work has to be spent. So this side, the performance of this refrigerator equal to T dash. T dash means minus 10 degrees centigrade, means 263. It is remembered that these temperatures are always in Kelvin scale and not degrees centigrade. And this T means 30 degree, 303 Kelvin, and minus 263 Kelvin. So this will be the efficiency. You can do by yourself. So this one 263 divided by 40. This is the efficiency. Or you can say 6.6 suppose. What does it mean? If we spend 1 calorie of heat, if we spend 1 calorie of heat or give this 1 calorie of heat to this refrigerator, it will extract 6.6 calorie of heat from inside of this refrigerator. And if you now this one actually Q dash divided by W. If you like to determine how much the heat will be extracted, so this Q dash equal to, in this case, equal to psi R into W, or this W equal to Q dash divided by psi R, and this is equal to 1000 calorie, and this psi R is 6.6. So this amount of this calorie of heat, this amount of work to be required to extract heat 1000 calorie from this LPR or inside this refrigerator. Now I am coming to this Carnot theorems or Carnot principles. And Carnot principle is shown in this diagram. This is H tier, this is A tier, same heat source, the same thing. We are here depicting this 3 engines. One is irreversible engine, another is a reversible engine, and this engine, the automobile engineers are trying to construct. The same amount of heat is given to these 3 engines from the same source, and LTR, the heat thrown to this LTR is like this: Q minus Wy, Q minus Wr, and Q minus Wp. So Carnot principle or Carnot theorem states that the efficiency of this irreversible engine is always less than efficiency of this reversible engine. Means efficiency of this irreversible engine and we construct the engines which are not perfectly reversible, perfectly ideal. So our engines are generally the irreversible engines. So efficiency of this irreversible engine is always less than reversible engine working between the same 2 reservoirs, thermal reservoirs. And And all, suppose if we take this two reversible engines, then also the efficiency of this one reversible engine is equal to the efficiency of this another reversible engine. Means, second theorem, all reversible engines are equally efficient working between these two definite thermal reservoirs. And this one, suppose eta E is greater than eta R, means we have constructed one engine which will be having the efficiency greater than reversible. So this, according to this Carnot principle, this efficiency is never possible to construct, and so this is impossible engine. This you can say a real engine, and this one can idealized Carnot engine. So three engines I write here side by side. This is the real engine that we can construct, whose efficiency will be less than the Carnot engine, and this is the reversible engine, maximum efficiency, and this one is impossible engine, could not be constructed in any way by any automobile engineer whose efficiency would be greater than the Carnot efficiency. Let us consider the two Carnot theorems or two Carnot principles. They could not be proved mathematically, but we can explain in terms of this logistic arguments. And two principles or two theorems are that a reversible engine is more efficient than an irreversible engine. This is one theorem. And second theorem, all reversible engines are equally efficient when working between the same two thermal reservoirs. For both the cases, we try to explain by putting some logic. Suppose here it is the H here. The criteria of this two engines are that heat taken by this irreversible engine Q, work done modulus of Wi. I now, without giving this a sign of this work done, it is given by arrow and it is the magnitude, and then it will be less trouble to deal mathematically. So it is the magnitude, and direction states that this amount of work is done by this irreversible engine. So the heat rejected Q minus Wi. And this reversible engine R, heat taken Q, same amount of heat is given to this engine. Work done is mod of WR, modulus of the WR. This is the magnitude, not the sign. And heat rejected equal to Q minus modulus of WR. Now, we shall have to prove that efficiency of this one is greater than efficiency of this reversible. Efficiency of this reversible engine has to be proved greater than the irreversible engine. That means the efficiency we have to prove the efficiency of this reversible engine is greater than efficiency of this irreversible engine working between the same two temperature limit. So if it is not possible, if it is not occurring, then the reverse, is true. If it is false, if this assertion is false, then the true assertion is the reverse one, means efficiency of this I is greater than efficiency of R. If we consider this one and build up a coupled engine, then we shall be able to prove that it violates the Planck Kelvin statements. This is the H tier, this is L tier, its temperature T, its temperature T dash, and this is the irreversible engine. Taken a heat, a Q from this H tier and doing mechanical work, Wi, and the rest amount of heat is rejected to this N tier. And this reversible engine, it is reversible means it can also work in a reverse way. So engine when works in reversible way, it becomes a refrigerator. So this refrigerator taking heat Q minus WR, and QR amount of heat is given to this refrigerator. Without putting the sign, we are putting direction, arrow. This amount of heat is done on this refrigerator. This amount of work is done on this refrigerator. This amount of work is doing this irreversible engines. So this Q amount of heat is thrown again to this HDR. So these two, whenever connected and self-connected, and this will give you a coupled engine. This gives this amount of work, and this is the amount of work required. So you can see there is no loss of heat of this HTR. Q amount of heat is taken and Q amount of heat again given to this HTR. So coupled engine is not drawing any heat to this HTR. And in case of LTR, say heat taken by the coupled engine. Coupled engine from LTR. From LTR at this temperature T dash equal to this one have been given and this one have been taken. So this how much heat is taken? Q minus W R modulus and minus Q minus modulus W I. This amount is taken, this amount is given. So this minus this minus this will give you the amount of heat taken by this coupled engine from this area. So simplifying this one, we can get this modulus Wi minus modulus WR. And the work done by the coupled engine. Here this amount of work is given, this amount of work we obtain. Then it will be equal to modulus Wi minus modulus WR. This amount of work is given and this amount of work we have obtained. So it is saying that the conclusion coming up, the amount of heat taken this one, amount of work done by this coupled engine also this one. It means that the heat is completely converted into mechanical work. This is not possible from this PK statement. Not only that, the heat is taken by one reservoir only, and this reservoir having no function. So this it is not possible, according to the PK statement, that no engine anyone can construct which is taking heat from one heat source and doing this mechanical work. So both the ways, heat cannot be completely converted into work, and heat cannot be completely converted into work by taking this heat from a single source, single reservoir. And the second one, if we consider, you can say this one, refrigerator can only be the reversible engines. Irreversible engine cannot be reversed. Irreversible engine cannot be reversed. So irreversible engine could not be acted as refrigerator and any time. So here the reversible engine we have used as a refrigerator, and irreversible engine is taken as engine. Then second one, suppose this one is R and this is R dash, and so the same amount of heat is given to this both are the reversible engines, and here I shall have to prove that the efficiency of this reversible engine is equal to this efficiency of this reversible engine. Both are equal. If it is false, if it is not true, then reverse is true. Reverse is true. Say eta R is greater than eta R dash. If we take this assertion and the given statement of this Carnot theorem suppose is false, then this will be true. Reverse is true. And in this case, this R and the work done is WR, and the heat rejected also WR. And in this case, this reversible engine now acting as this refrigerator. So this one also taken heat Q amount of heat taken. Here this will be this one and this one. Work done and work done by this way. In this case also work done. And this one is a refrigerator, so this one and this one and this is what I given modulus. Then also we can see the Q amount of heat is taken by this HTR, by this coupling. These are the two couplers. This is acting as this refrigerator and this one is the engine. This is doing what? And this work is supplied to this refrigerator or gas. So here there is no loss of heat to this HTR. Q is coming and Q is giving, and then amount of heat taken by this coupling in this case also from this HTR, and this one will be this we have received, and this one given means R dash. So this is the work obtained and this is the work given. So work obtained is this minus work of heat obtained. Heat is taken from this LTR. This one is taken Q minus W R dash, and this amount it is given Q minus W1. So it will be equal to this QR and QR dash. Amount of work done by this coupling, this amount of work we have received. So this is equal to WR, and this one given and WR dash. So in this case also it is seen that the heat is totally converted into mechanical work, and also taking this amount of heat from a single source, which is contrary to this Carnot, to this peak statement. So this one is false, this one is false, this one right. In this way we can explain the Carnot theorem in a geometrical fashion, and this is why it is also called sometimes the Carnot theorems. Carnot theorems. And now the one thing is left. The two statements, two very popular statements of the second law of thermodynamics, they are widely different, but it could be shown that they are equivalent in nature. Equivalent in nature. This is all about the Carnot refrigerator and the Carnot theorems. I have tried to explain these two in more or less details, and this is the last of this lecture today, and tomorrow or the next lecture I shall try to explain the equivalency of these two statements of the second law of thermodynamics, and also I shall give a brief explanation of this Kelvin scale of temperature. So thank you all who are watching this video, and if you like, please subscribe.